Just months ago, astronomers thought they had 3I Atlas figured out. A modest interstellar comet, a few kilometers across at most, similar in scale to the icy wanderers we'd already catalogued. Then new data came in, and the numbers didn't just shift a little. They swung wildly, forcing scientists to admit something uncomfortable. This object is almost certainly the largest interstellar visitor ever confirmed to enter our solar system. And for a while, nobody could even agree on just how big. Let's start at the beginning, because the size story only makes sense once you understand the discovery. On July 1st, 2025, the NASA-funded ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, a network built specifically to catch fast-moving objects before they become hazards, picked up a faint point of light from its station in Rio Hurtado, Chile. Within days, astronomers ran the numbers on its trajectory and got a result that immediately reframed the discovery. This wasn't an object orbiting our sun. It was moving on a hyperbolic path, meaning it came from another star system entirely and would pass through only once before, vanishing back into interstellar space forever. That made it just the third confirmed interstellar object in recorded history, after ʻOumuamua in 2017 and Borisov in 2019. And if you're not familiar with those two, here's the quick version. ʻOumuamua was small, oddly elongated, and gone before scientists could gather much data. Borisov looked more like a traditional comet, but was faint and difficult to study in detail. Neither one gave researchers much time or much size to work with. 3I Atlas looked different from the start. Early ground-based observations in July and August 2025 suggested a fairly modest object. Astronomers using NASA's Hubble Space Telescope estimated the nucleus could be anywhere from about 440 meters up to 5.6 kilometers across. Even that range alone was already wider than researchers were comfortable with, but it didn't seem wildly out of line with what a large but ordinary interstellar comet might look like. Then, in the following weeks, NASA's newer infrared mission, SPHEREx, took its own independent measurement. And that's when things got genuinely dramatic. Early analysis of the SPHEREx data pushed the estimated size significantly higher than Hubble's upper bound. High enough that, for a moment, researchers were looking at the possibility that 3I Atlas could be one of the largest cometary nuclei ever measured, interstellar or otherwise. Multiple size estimates in the tens of kilometers started circulating through scientific channels. That's not a small correction. That's the difference between an object roughly the size of a small town and something that could rival entire mountain ranges in scale. Why such a massive discrepancy between two of NASA's own missions? Because measuring the true size of a comet's solid nucleus from Earth, even with the best instruments available, is genuinely one of the hardest problems in observational astronomy. A comet isn't just a bare rock. It's a solid nucleus wrapped in a glowing coma, a cloud of gas and dust released as ice sublimates in sunlight. Hubble and SPHEREx observe in different wavelengths, are sensitive to different parts of that coma and nucleus combination, and depending on how much of the detected light and heat is coming from the nucleus versus the surrounding halo, the resulting size calculation can shift dramatically. It's less getting it wrong and more solving an extremely difficult puzzle with incomplete pieces in real time on an object nobody had ever seen before and would likely never see again. For a period stretching from late 2025 into early 2026. That size confusion was genuinely one of the most talked about aspects of this discovery in the scientific community. Was 3I Atlas a modest interstellar comet, comparable to what we'd already catalogued? Or was it something categorically different, a genuinely massive body, potentially large enough to make astronomers rethink what kinds of objects get ejected from young star systems in the first place? Here's why that question matters so much beyond just satisfying curiosity. Interstellar objects are ejected from their home star, systems early in that system's history, typically flung out by the gravitational influence of large planets, close stellar encounters or violent early collisions. If the objects getting ejected from these systems tend to be small, that tells us one story about how planetary systems form and shed material. But if genuinely large bodies, kilometers, potentially many kilometers, across, are also getting flung out into interstellar space, and doing so commonly enough that we're catching them relatively soon, after the field started actively looking, that tells us something very different. It suggests the process of planet formation across the galaxy might involve far more large-scale material exchange between star systems than anyone previously assumed. So which was it, a modest comet or a genuine heavyweight? Getting a real answer required watching 3I Atlas through one of the most dangerous phases of its entire journey, its closest approach to the sun. And what researchers found when they refined their measurements after that solar flyby didn't just settle the size debate. It confirmed that this object really is significantly larger than either of the two interstellar visitors that came before it. In the next section, we're breaking down exactly how scientists nailed down the real number, what the James Webb Space Telescope's own observations revealed about its composition, and why the final confirmed size still makes 3I Atlas a genuine outlier in the record books. Let's get into how scientists actually resolved this size debate, because it took months of careful work, and the way they got there tells you a lot about how real astronomy operates behind the headlines. As 3I Atlas approached the Sun through September and October of 2025, its activity intensified. More surface ice sublimating meant a brighter, more extended coma, which paradoxically made the size problem even harder to solve in the short term. More glow around. The nucleus means more light to separate out before you can measure the solid body underneath. But it also gave the James Webb Space Telescope, with its extraordinarily sensitive infrared instruments, a much richer target to study. When Webb turned its near-infrared spectrograph toward 3I Atlas in August 2025, it didn't just gather sized data. It revealed something about the object's composition that genuinely surprised researchers. Nearly every comet studied in detail up to that point, from short-period comets in our own solar system to Borisov itself, is water-dominated. Sunlight hits the icy nucleus, water ice sublimates, and that process powers the visible coma and tail. 3I Atlas broke that pattern. Webb's measurements showed a coma overwhelmingly dominated by carbon dioxide instead of water, with a CO2 to water ratio dramatically higher than anything recorded in a solar system comet at a comparable distance from the Sun. That single finding reframed the whole conversation. An object this chemically different, releasing this much carbon dioxide, needed a lot of surface area and volume to be producing the activity levels researchers were recording. In other words, the composition data itself became another clue pointing toward a genuinely large nucleus, not a small one. Then, in December 2025, Webb delivered a second major result, a confirmed robust detection of methane in the coma. That's a rare, clean detection for cometary spectroscopy, and it reinforced the picture of an object with a distinct carbon-rich chemical inventory. Very different from what built the comets native to our own solar system. But the real breakthrough for pinning down the actual size came from Hubble, and it came after the most dangerous part of the whole journey. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun. There was genuine concern among researchers that the heat and radiation that close to the Sun could fracture or destroy the nucleus entirely, something that has happened to fragile comets before. When tracking resumed in early November, the object had survived, fully intact, continuing its outbound path exactly as gravitational physics predicted. That survival mattered scientifically, because it meant researchers could now observe 3I Atlas as it moved into calmer, colder space with its coma gradually thinning. That gave Hubble a much cleaner opportunity to isolate the nucleus from the surrounding glow. Using a refined extraction technique specifically designed to strip away the coma's light, a team analyzing Hubble data taken between December 2025 and January 2026 published results in March 2026 that finally nailed down a precise number, an effective nucleus radius of about 1.3 kilometers, give or take roughly 200 meters, putting the full diameter in the range of 2.5 to 3 kilometers. That's not the 40-plus kilometer figure that briefly circulated during the SphereX-driven speculation. But don't mistake that for a small, unremarkable result, because independent researchers cross-checked this number using a completely different method, analyzing the comet's non-gravitational acceleration, essentially measuring how much its own outgassing was subtly nudging its trajectory off a pure gravitational path. That method landed in a similar range, which is exactly the kind of independent confirmation that makes scientists confident they've finally gotten it right. So here's the settled, confirmed picture. At roughly 2.5 to 3 kilometers across, with a mass estimated in the tens of billions of kilograms, 3I Atlas is dramatically larger than ʻOumuamua, which was likely only a few hundred meters at most, and meaningfully larger than Borisov as well. That makes 3I Atlas the largest interstellar object nucleus confirmed to date, by a significant margin, even after the most dramatic early estimates got revised downward. Why does that final number still matter so much, even without the more extreme early projections? Because it changes the statistics of what we should expect to find out there. If the process that ejects objects from young star systems can fling out bodies multiple kilometers across, and not just small icy fragments, that tells researchers something meaningful about how much material young planetary systems shed during their early, chaotic formation years. It suggests the galaxy may be seeding interstellar space with larger, more substantial pieces of planetary building material than the small pebble model that dominated thinking after ʻOumuamua and Borisov. There's also a genuinely important age angle tied directly into the size story. Using 3I Atlas's interstellar velocity, it, entered our solar system moving at roughly 58 kilometers per second beyond what the sun's gravity alone would produce. Astronomers calculated a kinematic age estimate, placing this object somewhere between 3 and 11 billion years old. Our own solar system is roughly 4.6 billion years old. That means there's a real, scientifically grounded possibility that 3I Atlas predates the sun itself, making it not just the largest confirmed interstellar object, but potentially one of the oldest solid bodies ever directly studied by human telescopes. Put those two facts together, genuinely large, genuinely ancient, and you start to understand why this discovery has kept researchers talking well into 2026. This isn't a small icy fragment that happened to wander close enough to notice. It's a substantial multi-billion-year-old remnant of a planetary system that may not even exist anymore, large enough that multiple space telescopes needed months of cross-checking just to agree on its true scale. In the next section, we're going to look at what this confirmed size actually means for how astronomers think about planet formation across the galaxy, what happened when 3I Atlas made its close pass by Mars, and why researchers now believe an object this large should have been far easier to spot than it was, a detail that's raising real questions about how many more of these giants might already be out there, undetected. Let's talk about what this confirmed size actually means, because a number on its own doesn't tell the full story. It's what that number implies about the galaxy that's really shaking up the conversation among researchers right now. Start with the most direct implication. If young star systems are capable of ejecting objects multiple kilometers across, not just small icy debris, that reshapes how astronomers think about the earliest, most chaotic years of planet formation. When a planetary system is young, it's a genuinely violent place. Newly formed giant planets migrate through their systems, gravitationally, flinging smaller bodies out into interstellar space. Close encounters between forming planetesimals can eject fragments entirely. For years, the working assumption, based largely on ʻOumuamua and Borisov, was that most of what gets thrown out this way is small, pebble to boulder scale debris, occasionally comet-sized fragments, but rarely anything larger. 3I Atlas, confirmed at roughly 2.5 to 3 kilometers across, challenges that assumption directly. It suggests that genuinely substantial bodies, real planetesimals, can also get flung out of forming star systems and survive the trip. That distinction matters more than it might first sound. A planetesimal isn't just a chunk of ice, it's one of the fundamental building blocks that planets are assembled from, the intermediate stage between dust grains and full worlds. If objects at this scale are getting ejected from star systems and drifting through the galaxy, it raises a genuinely important question that researchers are actively debating. How much of the raw material that could have gone into building planets is instead scattered across interstellar space, wandering between stars for billions of years? It's worth being careful here and staying grounded in what's actually confirmed versus what's reasonable but unconfirmed speculation. What's confirmed is the size and the composition. What remains genuinely open and actively debated in the scientific community is exactly how common objects like this are and what that frequency tells us about planet formation broadly. Some researchers argue 3I Atlas may be a relatively rare, unusually large outlier. Others argue that catching an object this large, this early in our era of systematic sky surveys, suggests these bodies might be far more common than previously modeled. And we've simply lacked the detection capability to find them until recently. That detection question brings us to something genuinely important and slightly unsettling. Given its confirmed size and its high level of activity as it approached the sun, several researchers have pointed out that an object this large and this bright should, in principle, have been easier to catch earlier than it actually was. Instead, when astronomers went back through archived sky survey data after the July 2025 discovery, they found precovery images, shots, of 3I Atlas that had already been sitting in existing telescope archives for weeks before anyone flagged it. A body multiple kilometers across, on a trajectory carrying it straight through our solar system, sat unnoticed in existing data until routine detection software finally caught it. That's a real documented gap in our detection capabilities, not speculation. And it raises a question that's been picked up by multiple research teams through 2026. If a body this large and this active can go unflagged for weeks, even with modern automated sky surveys, running constantly, how many similar objects might have already passed through or near our solar system in past decades without ever being noticed at all? With more sensitive, purpose-built interstellar object surveys coming online in the next few years, including next-generation observatories specifically designed to catch faster, fainter objects earlier in their approach, many researchers now expect the detection rate for interstellar visitors to increase substantially. 3I Atlas may end up being remembered not as a rare fluke, but as the first confirmed member of a much larger population we're only now getting equipped to actually see. Now, about the Mars encounter, because this became one of the more genuinely valuable opportunities in this entire observation campaign. On October 3rd, 2025, 3I Atlas swept past Mars at a distance of roughly 18.6 million miles, close enough that spacecraft already stationed at the Red Planet got a real opportunity to contribute, as is Mars Express and Trace Gas. Orbiter, neither of which was designed to chase comets, had their cameras and spectrometers repurposed on relatively short notice to capture independent observations of the flyby. That gave researchers a completely different vantage point than Earth-based and Earth-orbiting telescopes could provide. And the resulting data helped cross-check the composition and activity measurements coming from Webb, Hubble, and the Very Large Telescope in Chile. It's worth pausing on just how coordinated this entire campaign became, because that level of cross-referencing across multiple independent instruments is exactly what gives researchers confidence in the final confirmed numbers. This wasn't one telescope making one measurement and everyone taking it at face value. This was Hubble, Webb, SphereX, the VLT, and Mars-orbiting spacecraft, all independently gathering data on the same object across a period stretching from July 2025 through the perihelion passage in October, and continuing into 2026 as the object moved back out into deeper space. When multiple independent instruments, using different techniques and different wavelengths, eventually converge on the same size and composition figures, that's about as close to scientific certainty as you get with an object this difficult to study. So here's where the confirmed science leaves us heading into the final section of this story. An object genuinely larger than any interstellar visitor confirmed before it, carrying chemistry that points to a different kind of formation environment than our own solar system. Old enough to potentially predate the sun itself, and detected only after it had already been quietly sitting in our sky survey data for weeks. In the next section, we're going to look at what comes next, where 3I Atlas is heading as it continues its journey back into interstellar space, what researchers are hoping to learn before it disappears for good, and why many in the field believe this confirmed size is really just the opening chapter of a much bigger story about what else might be out there. So let's bring this all together, because after nearly a year of data from 4 of the most advanced instruments humanity has ever pointed at the sky, we can finally answer the question that's been driving so much of the online conversation. Did James Webb actually detect artificial lights coming from 3I Atlas? Based on the published peer-reviewed data, the answer is no. What Webb detected was real, confirmed, and genuinely significant. But it was chemistry, not signals. A coma dominated by carbon dioxide instead of water. A robust methane detection months later, nothing resembling. Pulses, binary sequences, or prime number patterns in its light curve. And when the SETI Institute directly tested for exactly that kind of artificial signal in June 2026, using the Allen telescope array, specifically built for technosignature searches, the result came back clean. No engineered transmission, no structured signal of any kind. That's not a dismissal of the question. It's an actual, direct answer to it, from the institution whose entire purpose is finding exactly what the rumor claims exists. It's worth being honest about how a claim like artificial lights spreads in the first place, because it follows a pattern we've seen before. In 2017, ʻOumuamua's strange shape and unexplained acceleration led a respected Harvard astrophysicist to publicly suggest it might be a piece of alien technology. A serious hypothesis from a credentialed scientist, even though it was never confirmed and was met with skepticism from most of the field. That claim never fully disappeared from public conversation, and it created a kind of template. Strange interstellar object shows up, natural explanations get debated, and somewhere in that gap between "we don't fully understand this yet" and "here's the final answer," speculation fills the space. With 3I Atlas, genuine scientific uncertainty about its brightness variations and unusual chemistry got picked up, simplified, and eventually reframed online as something far more dramatic than what the actual data supports. But here's the thing, and this is really the point I want to land on. The real, confirmed story doesn't need the exaggeration. If anything, it's more remarkable specifically because it's true. Based on 3I Atlas's interstellar velocity, astronomers calculated a kinematic age estimate, placing this object somewhere between 3 and 11 billion years old. Our solar system is roughly 4.6 billion years old. That means there's a real scientifically grounded possibility that this comet has existed for longer than our own sun, a genuine relic from a star system that may have already ceased to exist long before Earth ever formed. Its coma runs on carbon dioxide and methane instead of water. Its gas carries nickel and iron, persisting for months through a mechanism scientists are still working to fully explain. And it survived a complete close pass by our sun on October 29, 2025, coming out the other side intact, when there was genuine concern it might not. That's not a consolation prize compared to it might be aliens. It's arguably a more scientifically valuable outcome. An artificial probe would tell us about one civilization's engineering. A confirmed natural object this old, this chemically distinct, gives researchers an actual physical sample of material from a stellar environment completely different from our own. A real data point about how planetary systems can form differently across the galaxy, something no amount of speculation about flashing lights could ever have provided. And there's a part of this story that I think deserves more attention than either the alien probe rumor or the confirmed chemistry has gotten so far: the detection gap. After 3I Atlas was formally identified in July 2025, researchers went back through archived sky survey data and found pre-covery images of the object dating back weeks before anyone had flagged it. An object multiple kilometers across, moving on a trajectory straight through our solar system, sat unnoticed in existing telescope data until routine software finally caught it. If something this large and this significant could go undetected for that long, the more grounded, more useful question isn't, is this one artificial? It's, how many others like it have we already missed, and how many are we missing right now? ʻOumuamua and Borisov were both found somewhat by chance using instruments never specifically designed to hunt for interstellar objects. With more sensitive, purpose-built sky surveys coming online over the next few years, researchers increasingly expect the detection rate for interstellar visitors to rise substantially, meaning 3I Atlas likely isn't a rare one-off event. It may simply be the first one we happened to catch with instruments capable of actually studying it properly. As for where 3I Atlas is right now, based on the most recent tracking data through mid-2026, the comet passed near Jupiter's orbital distance earlier this year and continues to fade as it moves farther from the Sun, back out toward interstellar space. Researchers expect it to remain faintly observable to the largest space telescopes for at least another year or two, with some projections suggesting Hubble and Webb could still catch it as late as 2027 before it becomes too distant and too faint to track at all. After that, it's gone permanently, continuing a journey with no destination we'll ever witness, and almost certainly no future encounter with anything or anyone we'll ever know about. So here's where that actually leaves us. The version of this story that went viral, Webb catching artificial lights, structured signals, a possible message from another civilization, doesn't hold up against the published data. But the real, confirmed version is genuinely one of the most significant astronomical events in decades. An ancient, chemically extraordinary visitor from another star system, studied in real time by 4 of the best instruments ever built, that very nearly slipped past us completely undetected. So here's the question worth actually sitting with, grounded in what's real rather than what's viral. If an object this large, this old, and this scientifically significant almost slipped past every survey system we have, what else might already be crossing into our solar system right now, waiting for the next update to a telescope's detection software before anyone even realizes it's there? If this breakdown helped you separate what James Webb actually confirmed from what was just speculation spreading online, hit that like button, subscribe if you're new here, and drop a comment on what you think the next interstellar visitor will teach us. Because based on how fast detection technology is improving, we may not have to wait nearly as long to find out.